If you are learning Python right now, or diving into data science for the first time, your setup probably looks identical to like thousands of other people.
Oh, absolutely. The classic setup.
Right. You have a Jupyter notebook open on your screen. You've gone to a repository like Kaggle, found some fascinating problem to solve, and you downloaded this beautiful, pristine, perfectly formatted CSV file.
Yep. The dream scenario.
Exactly. You write your import pandas as PD, you load that file into a data frame, you type dsv.head, and boom, there it is. A clean, rectangular grid of data.
No missing values.
No weird anomalies, no formatting issues, just rows and columns sitting there perfectly in your laptop's memory. And it feels incredible, right? It feels like you are doing real machine learning.
It does, but we need to pop that bubble today.
We really do. Because I have a harsh reality check for you today. In the real world, that pristine CSV file does not exist. It is a total myth. Machine learning engineers in actual production environments almost never receive data in this convenient prepackaged form. Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry ready and apply your knowledge to real industry projects.
And that realization that the pristine CSV is an illusion, it's usually the very first major hurdle a junior engineer hits when they land their first real job.
Oh, totally. It hits them like a truck.
Right, because we spend all this time in academia or online courses optimizing algorithms, tuning hyperparameters, building these complex neural networks.
But we operate under this false assumption that the data will just be like handed to us on a silver platter.
Exactly. But the reality is that enterprise data lives, breathes, and constantly mutates inside highly complex relational databases. So the goal of our deep dive today is to completely tear down your existing mental model of data and basically rebuild it from the ground up.
Which is so necessary.
It is, because if you want to build machine learning models that actually drive business value, you have to understand the architectural habitat where your data is born.
I really want to visualize this habitat for a second because the contrast between a static file and a living system is pretty jarring.
It's night and day.
Let's imagine a massive e-commerce platform during a high-traffic event, like Black Friday.
Oh, pure chaos.
Pure chaos. You have millions of concurrent users. People are logging in from different devices. They're adding items to their carts, removing items, trying to apply expired promo codes, processing credit cards.
Refreshing the page frantically when the site lags.
Exactly.
Yeah.
Now, if a company tried to just append all of that chaotic, high-velocity activity to one gigantic, endless Excel spreadsheet, the file would corrupt instantly.
Oh, yeah. The read and write locks alone would just bring the entire server to a grinding halt.
So software engineers obviously don't build systems like that. They fragment the business. They break the entire universe of the e-commerce platform into multiple, distinctly separated but logically connected areas.
Oh, yeah, they compartmentalize it.
Yeah, you have an area dedicated exclusively to user profiles, another area strictly for inventory and products, and then another area just recording the microscopic details of every mouse click and screen scroll.
And that fragmentation, that's the foundational reality of software engineering, which, by extension, dictates the reality of machine learning engineering.
Because we have to work with what they build.
Exactly. The models we want to build, say an algorithm that predicts whether a user is going to abandon their shopping cart, they require a holistic view of the user.
Right.
But the raw data required to build that complete view is scattered across a dozen different isolated systems. You are not handed the final flat feature matrix.
You're just handed the keys to the warehouse.
You're handed the keys, and you have to know how to navigate the aisles, extract those raw materials, and assemble the dataset yourself. Understanding how this architecture is structured is the absolute prerequisite to feature engineering.
So we really need to understand how software architects look at the messy, chaotic reality of millions of shoppers and translate that into a structured data system. Like, how do they decide what gets fragmented and where it goes?
Well, it all comes down to identifying what we call entities.
Entities, okay. I know this traces back to like the 1970s and the invention of the relational database, but what is the actual conceptual framework they're using here?
So the conceptual framework revolves entirely around mapping the business model. Before a single line of code is written, database architects look at the business and identify the core nouns that make up that specific universe.
The nouns, I like that.
Yeah, an entity is basically an independent object or concept that has a distinct existence. So in our e-commerce scenario, the system architects determine that a user is a fundamental noun.
Right, and a product is a noun.
Exactly. An order is a noun. A payment is a noun. They are essentially mapping the ontology of the business.
It's almost like they're defining the physical laws of their digital universe, right? They're deciding what things are officially allowed to exist.
That's a great way to put it.
So once they define these nouns, these entities, how does that translate into the actual storage mechanism? Like, where does the data go?
Okay, so once the entities are defined, each one is assigned its own dedicated, isolated space. We call this structure a table.
A table. Got it.
And the mandate here is strict isolation. All the information that defines a user must live in the user's table
Right.
and absolutely nowhere else.
And all the info about a product lives only in the products table.
Exactly. This concept, which was born from Edgar Codd's relational model back in the day, solved a massive historical problem called the update anomaly.
Oh, right. Because if we use that giant flat spreadsheet we talked about earlier.
Yeah, imagine if a user named Sarah moves to a new apartment, and we have her 50,000 individual clicks and purchases recorded in a flat file. We would literally have to search for and update her address 50,000 separate times.
Which is a nightmare.
A total nightmare.
Yeah.
But with the entity table model, Sarah exists in exactly one place, the user's table. If she moves, we update her address once, and the entire system instantly reflects that change.
That makes perfect sense from like a software engineering and storage efficiency standpoint. We isolate the nouns to prevent chaos.
Precisely.
But let's put on our machine learning hats now and zoom in on one of these isolated rooms. If I open up the users table, I'm looking at a grid. It has rows and it has columns. From a database perspective, a row is just a record.
Right.
But what exactly does one single row represent in this architectural model?
So a row represents one single specific instance of an entity. It is a unique manifestation of the noun.
Okay, so if the entity is the abstract concept of a user.
Then a single row in the user's table is a literal human being sitting at their computer. It is user ID 4092 who signed up on a Tuesday.
I see. And if the table is the products table?
Then a single row is not the abstract idea of footwear. It is the specific red Nike running shoe, size 10, sitting in warehouse aisle 4. The table defines the category, but the row represents the physical or digital reality of one item in that category.
Okay, and running perpendicular to those rows, we have the columns. So if the row is the specific human or the specific shoe, the columns are the attributes.
Yes, they describe the instance.
So for a user, the columns are their age, their sign-up date, their hash password, their country of residence.
Exactly.
But here is where we really have to make a massive psychological shift for anyone listening who wants to do machine learning.
This is the critical part.
Because when a database administrator looks at a column named age, they are thinking about storage optimization. They're thinking, I can store this as an 8-bit integer to save disk space.
Right, they're thinking purely about infrastructure.
But when I look at that exact same column, I am not thinking about disk space. If I'm building a model, these columns aren't just data points. They are my features, right?
Yes. The shift in perspective is everything. Columns become features. In the context of a predictive model, a column is an independent variable. It's a mathematical signal.
So it's input data for the algorithm.
Exactly. If you're trying to build, say, a logistic regression model to predict the probability that a user will purchase a premium subscription, your model is trying to solve a complex equation. The columns in the database like age, country, account tenure, those become the inputs to that equation.
You're asking the algorithm to look at the variance within that age column and find statistical correlations with the target variable.
You've got it. The database table is not just a digital filing cabinet. It is a menu of raw predictive signals just waiting to be exploited.
Well, let's lock this mental map in place because it is the bedrock of everything we will do moving forward.
Let's do it.
We observe a chaotic real-world system. We analyze it and identify the core nouns, which we call entities. We give every entity its own isolated storage space, called a table.
Right.
Inside that table, every specific physical or digital instance of that entity gets its own row, and every descriptive characteristic of that instance gets a column.
Which we, as machine learning engineers, will mathematically evaluate as a feature.
Exactly. That pipeline from reality to algorithm is the essence of data modeling.
It is. But I have to warn you, simply knowing that tables exist and hold features is only scratching the surface.
Uh-oh. Here comes the catch.
The moment you start trying to extract these features and feed them into a Python script, you are going to encounter a structural landmine that destroys the models of almost every junior engineer.
Oh, I know exactly what you're referring to. I'm thinking about the schema of our e-commerce database right now.
Tell me what you see.
Well, I see the users table, and a row represents one person. Cool. Simple enough. But then I look at the clicks table, and a row represents, like, a single millisecond where someone moved their mouse over a button. Those are two fundamentally different scopes of reality. Treating them as if they're mathematically equivalent in a data set just feels like a massive mistake.
It is a fatal mistake,
Yeah.
and it introduces the formal concept of granularity.
Granularity.
Yes, granularity dictates the level at which a table operates. It defines the exact scope of a single row within any given table. And if you fail to account for the granularity of the tables you're pulling data from, your machine learning model won't just be slightly inaccurate.
That would be a disaster.
It will be mathematically corrupted by statistical bias.
I like to think of granularity as the zoom level on a microscope. Let's put some different tables under the lens to see how this zoom level actually changes.
I love that analogy.
So if we look at the users table, the microscope is zoomed pretty far out. The granularity is one row equals exactly one user. If the business has 10 million registered accounts, that table has exactly 10 million rows. It's a clean one-to-one relationship.
Right, but slide the Petri dish over and look at the orders table. The zoom level increases dramatically. In the orders table, the granularity is one row equals one distinct purchase event. A single user from our 10 million row users table might be a power shopper who's placed 50 distinct orders over the past 3 years.
Wow, okay.
Therefore, that single individual human being is represented by 50 separate rows in the orders table. The granularity is much finer.
And we can zoom in even further, right?
Sure.
Let's look at the sessions table.
Let's do it.
A session is created every time someone opens the app on their phone or navigates to the website. Now, that power shopper who made 50 purchases probably didn't buy something every single time they opened the app.
Definitely not.
They might have browsed the site 500 separate times just to make those 50 purchases. So for that one single human being, we have one row in the users table, 50 rows in the orders table, and 500 rows in the sessions table.
And at the absolute maximum magnification, we have the clicks table. This is often referred to as the event stream or telemetry data.
And here the granularity is totally microscopic.
Exactly. One row equals one specific interaction. Scrolling down a product page, hovering over an image, adding an item to a cart, removing it 5 seconds later.
So that power shopper with their 500 sessions,
They might have generated 80,000 individual rows in the clicks table.
this disparity in volume is staggering. One row versus 80,000 rows describing the exact same person.
So let's bring this back to the Python environment. Why does this disparity mathematically break a machine learning model if we aren't careful?
Let's visualize how a supervised learning algorithm, say a random forest or a deep neural network, actually learns.
Okay.
These algorithms require a flat two-dimensional matrix to train on. They expect a consistent grain. If you're building a model to predict user churn, meaning whether a person will cancel their account, the algorithm expects exactly one row per user.
It wants to look at user A, assess their features, and see the outcome.
Exactly. Then it looks at user B, assesses their features, and sees the outcome. It assumes each row holds equal weight as a distinct observation. Ah, I see the trap. So if I want a feature that captures a user's shopping behavior, and I just try to blindly merge the users table with the orders table without adjusting the granularity, I've ruined the data set.
You've completely ruined it. The database engine will duplicate the user's profile for every single order they made.
So user A, who bought one thing, gets one row. But user B, our power shopper who bought 50 things, gets duplicated 50 times in my training matrix.
And the mathematical consequence of that is disastrous.
Well,
Your random forest algorithm doesn't know that those 50 rows represent the same human being.
it just thinks there are 50 different people who all look exactly like user B.
Right. It just sees 50 distinct observations of a person with user B's exact age and demographic profile. The model will statistically overweight user B's characteristics during training simply because they occupy more physical space in the matrix.
Wow.
Your model becomes heavily biased toward the behavior of frequent shoppers, entirely destroying its ability to generalize to the broader user base.
The model is effectively being brainwashed by volume.
Brainwashed by volume. That is exactly what happens.
So the mandate is clear. The database stores data at a highly granular microscopic level to capture reality, but our predictive models, demand a low granular macro level view to maintain statistical fairness.
Yep.
We have to somehow bridge that gap. I'm assuming this means we have to somehow squish or compress those many rows into one row. Like take those 80,000 clicks or 50 orders and format them so they fit onto a single row for that user.
Yes. And the technical term for that compression is aggregation.
Aggregation. Right.
It's the act of taking high granularity data and mathematically summarizing it to match a lower granularity target. You take the 50 rows representing individual purchase amounts from the orders table, you apply a mathematical function like a sum, and you produce a single scalar value.
Like total lifetime spend.
Exactly. Or you take the 80,000 rows from the clicks table, you apply a count function filtered by the last 30 days, and you produce a single feature clicks past 30 days.
So aggregation isn't just some minor pre-processing step. It is the absolute heavy lifting of feature engineering.
It's basically the whole job.
You are acting as a translator, taking the raw, hyper-detailed language of the database and summarizing it into the dense, singular signals that an algorithm can actually understand.
Beautifully said.
But this process introduces a terrifying logistical vulnerability to me.
How so?
Well, if I am pulling a user's age from the users table, summing up their purchases from the orders table, and counting their activity from the clicks table, how on earth do I guarantee that I am not attaching a teenager's frantic click history to their grandmother's profile?
The identity problem.
Yeah. How does the database prevent a catastrophic mix-up of human identities when we're squishing data together from all these different rooms?
That is where the architectural genius of the relational model really shines. To allow data to be fragmented into different tables without losing the cohesion of the real world, databases employ a rigorous system of identifiers called keys.
Keys, okay.
And the foundation of this system is the primary key. A
Yeah.
primary key is a specialized column within a table that has one job and one job only: to provide an absolute, mathematically guaranteed unique identifier for every single row in that specific table.
So I think of the primary key like the VIN number stamped onto the chassis of a car.
Oh, that's a perfect analogy.
Right, because a car might get repainted, the engine might be swapped, the owner might change, but the VIN number is permanently etched into the metal. It is the absolute identity of that vehicle.
Exactly.
So in our database, the user ID is the VIN number for the human. User ID 9942 is a specific person. And the database engine enforces a strict constraint, right? It guarantees no duplicates. It's physically impossible for two rows in the user's table to possess the same primary key.
That strict constraint is exactly what allows us to safely engineer features. When you do the hard work of aggregating 50 orders into a total lifetime spend metric, you aren't just holding a random number in the void.
You're holding a value permanently bound to that specific user ID.
Exactly. The primary key is the anchor point. You engineer the feature, and you bolt it securely to the anchor.
It's like a physical coat hook. In ML, the primary key is the literal hook we use to hang all our newly engineered features on. We attach total orders or day since last login right onto user 9942's hook.
I like the code hook visual. But the primary key only solves the identity problem within a single, isolated table. It doesn't explain how the tables talk to each other.
Right. Because my newly engineered total lifetime spend feature didn't originate in the users table. I calculated it using data all the way over in the orders table.
Exactly.
So how did the orders table know which user was making the purchase at the exact moment of checkout? If the tables are isolated rooms, how does the information cross the hallway?
It crosses the hallway using the second half of the architecture, the foreign key.
Okay, so primary keys and foreign keys.
Yes. If the primary key is the VIN number stamped on the car, the foreign key is the mechanic's ledger.
Oh, interesting.
When you take your car into a shop for a brake replacement, the mechanic doesn't write down the entire blueprint of your car, or the color of your interior, or your home address. They simply write down the date, the repair performed, and the car's VIN number.
So they just use the identifier to link the event to the object.
Exactly. In our database, a foreign key is a column in one table that explicitly stores the primary key of a different table.
Got it.
If we look inside the orders table, every row has its own primary key in order to identify the specific transaction, but it also contains a column named userid. That column is a foreign key.
Oh, so it's a pointer.
It's a mathematical pointer that declares the entity responsible for this specific transaction is the entity holding primary key 9942 over the user's table.
This is where the fragmentation of the database becomes beautiful rather than chaotic, because these foreign keys act as a breadcrumb trail that allows us to reconstruct the story of a user's behavior. We can literally stitch reality back together.
That's exactly what you're doing.
As a machine learning engineer, you're essentially an investigator following this trail. Let's say you want to build a feature predicting if a user will buy a specific brand of shoes. You start at the user's profile. You use their userid foreign key to traverse into the sessions table to see when they were online.
Yep.
From there, you use the sessionid foreign key to traverse into the clicks table to see what pages they viewed during that session.
Following the crumbs.
Then you use the producted foreign key in the clicks table to jump into the products table to check if the pages they viewed were actually categorized as shoes. You use the keys to weave all these fragments into a cohesive narrative.
And professional teams, they don't just try to hold this massive web of relationships in their heads.
I would hope not.
No, they use an architectural blueprint called a schema graph. It is a visual diagram, much like an electrical schematic or a city transit map, that details exactly how every single table is wired together.
It visually maps how the entities connect.
Exactly. It shows a box for the users table, with a line representing the foreign key relationship drawn down to the orders table, and another line drawn over to the sessions table.
You know, I always hear junior developers call the schema graph a treasure map, but I honestly think that implies you're just wandering around hoping to find something valuable.
Right, like it's based on luck.
Yeah, but it's much more rigid than that. It is an engineering schematic. When a product manager asks you to build a recommendation engine, you don't guess where the data is. You consult the schematic.
You trace the wires.
Exactly. You trace the physical wiring from the target variable you want to predict, backward through the foreign keys, to the raw signals scattered across the tables. But, as you look at the schematic, you start to realize that the tables don't all behave the same way in real time.
They really don't.
Like, they seem to have different temporal physics.
That is a critical observation, and it leads perfectly to the next major conceptual divide in data modeling. When you observe a live database, you will see that tables generally fall into two distinct behavioral categories: state tables and event tables.
State and event.
Yes. And failing to understand the difference between these two will lead to features that leak future information into the past, which completely invalidates your models.
Let's define the first category then. State tables.
State tables are designed to capture the current resting attributes of an entity. They basically represent a snapshot of reality at a specific moment.
So the classic examples are the anchor tables we've been discussing, right? Users, products, store locations.
Yep.
But what is the defining physical characteristic of a state table when you observe it in a production environment?
It's mutability and slow velocity. State tables are meant to be updated, overwritten, or mutated as the real world changes.
Okay, so the values here change slowly.
Exactly. Let's look at a user's account profile. Their sign-up date is established once and never changes. Their date of birth never changes. Their billing address might change once every 3 years if they move.
Their loyalty tier might be updated from silver to gold once a year.
Right. The data in a state table is relatively static. The number of rows grows slowly, usually only when a brand new user joins the platform.
Okay, so contrast that slow, deliberate mutation with the absolute chaos of the second category. Event tables.
The event tables are the exact opposite. They're immutable activity logs. They record specific actions or transactions that occur at a precise point in time.
A purchase, a page view, a password reset request.
A server error. Yes. And the defining characteristic of an event table is sheer, relentless velocity and scale.
Because they're constantly growing with every user action.
Massively. A state table might add 1,000 rows a day as new users sign up. An event table tracking API requests might add 1,000 rows every second. Furthermore, because an event is a historical fact, it is immutable. If a user clicks a button at 4:02 p.m., you cannot go back and update that click. It happened. It is forever etched into the log. Every single row in an event table is fundamentally bound to a timestamp.
Okay, so how do these two table types interact when building a model? What's the feature engineering recipe here?
So there is a foundational paradigm, often considered the golden rule of feature engineering in relational systems. Almost all predictive power in machine learning comes from taking the massive high-velocity event tables, aggregating their massive amounts of rows, and attaching those summaries back onto the slow-changing state profiles.
So like taking thousands of click events, summing them up, and attaching total clicks to the user's state profile.
That is the exact recipe.
Let's walk through a highly specific, high-stakes case study to see this golden rule in action.
I'm ready.
Imagine it's Black Friday. We work for a major payment processor, and we need to deploy a machine learning model that detects credit card fraud in real time.
High stakes indeed.
The model needs to evaluate a transaction the exact moment the user clicks buy. We look at the state table, the user profile. It tells us the account is 4 years old, the user lives in Chicago, and they are in the gold loyalty tier.
Which is a static snapshot.
Exactly. It's completely useless for predicting if the person currently holding the mouse is a hacker who just stole the password.
Right, because the static state provides context, but it lacks the behavioral signal necessary to detect an anomaly. A hacker looks identical to the legitimate user on paper.
They both live in Chicago with a 4-year-old account.
Exactly. To find the anomaly, you must analyze the velocity and pattern of recent actions. You have to query the event tables.
So we apply the recipe. We don't just look at the user's name, we look at the raw authentication logs, which is an event table. We write a query that isolates the specific user ID, filters for events that occurred in the last 10 minutes, and counts the number of failed password attempts.
We aggregate the events.
Yes, we get a value, say, failed logins 10 meetings equals 5. Then we look at the clicks event table, filter for the last 5 minutes, and calculate the physical speed of the mouse movements, generating another feature. Say, average time between clicks equals 0.2 seconds.
And then the crucial step.
We take these aggregated behavioral signals and we bolt them onto the static user profile. Now, our fraud model isn't just looking at a 4-year-old account from Chicago.
It's looking at an account from Chicago that just failed its password 5 times and is navigating the checkout page at superhuman bot-like speeds.
That is the essence of feature engineering right there.
Uh-huh.
You are extracting behavioral signals from the chaos of the event stream and structuring them into mathematical predictors attached to the state entity.
It's beautiful and it works. But, understanding this recipe conceptually is only half the battle.
Right. We have to actually build it.
We now have to discuss the actual machinery used to execute this process. How do we physically take billions of rows of event data, aggregate them, and join them to a state profile to create that final data set for Python?
Let's zoom out and look at the entire assembly line. How does raw database data actually turn into the data set we feed our Python model? Because I guarantee a lot of listeners who are already comfortable with Python might be thinking, this sounds easy. I'll just pull all these raw tables into Pandas and do my filtering and joining there.
Oh boy. I have seen brilliant data scientists bring entire company networks to their knees operating under that exact assumption.
Really?
It is a fundamental misunderstanding of computational architecture. Let me share a battle scar from my early career, or rather, a mistake I watched a very confident junior engineer make.
Do tell.
They were tasked with building a churn prediction model. They needed to analyze user sessions. The sessions event table contained about 2 years' worth of historical web traffic, roughly 3 billion rows, taking up about 150 gigabytes of disk space.
Oh, I can already see where this is going.
This engineer opened their laptop, which had like 16 gigabytes of RAM. They wrote a simple Python script, pandas.read SQL, select from sessions.
Yeah.
They instructed Python to reach out to the production database, pull all 3 billion rows across the network, and load them into the laptop's volatile memory.
The physics just don't work. You can't put 150 gigabytes of water into a 16 gigabyte bucket.
Exactly. First, the network choked trying to transmit that much raw data. Then, as Pandas desperately tried to allocate memory, the laptop's operating system started paging memory to the hard drive, the fans spun up like jet engines, the Python kernel crashed completely.
And I'm guessing the database wasn't too happy either.
That was the worst part. The massive, unoptimized query locked up resources on the production database, slowing down the actual website for real customers.
That is a critical industry insight right there. Python is an incredible tool for statistical modeling and matrix multiplication, but it is fundamentally not designed to process the raw, unaggregated universe of an enterprise business in memory.
No, it's not. And this is why the industry relies on a completely different piece of machinery to do the heavy lifting. We use the SQL Feature Engineering pipeline. Modern data warehouses, systems like Snowflake, Google BigQuery, or Amazon Redshift, are not just storage lockers.
They're supercomputers.
They are distributed, highly parallelized supercomputers specifically engineered to scan billions of rows in seconds. The absolute golden rule of professional data science is this. You push the computation down to where the data lives. You do not bring the data to the computation.
So you use SQL to command the database supercomputer to do all the joining, filtering, and aggregating internally.
Exactly.
Oh.
You only extract the final compressed, highly aggregated feature matrix into Python.
I like the analogy of an ML dataset factory. The raw materials, the billions of events, enter at the top of the SQL factory. The data flows through a series of highly optimized, specialized assembly stations, each powered by a specific SQL operation. And a shiny, model-ready feature dataset rolls out at the bottom.
Let's walk the factory floor and look at these stations conceptually, step by step, because this is the actual pipeline an ML engineer builds every day.
Let's do it. The first station the raw data hits is usually projection.
Right. Projection is the act of selecting columns to narrow the horizontal scope. An event table might have 80 columns, tracking everything from the user's IP address to the exact pixel coordinates of their mouse.
But for our fraud model, we only care about the timestamp and the action type.
Exactly. So we use a SQL statement to project only those two columns, immediately discarding massive amounts of irrelevant data from the pipeline.
Got it. Once we've narrowed the columns, the data moves to the filtering station. This narrows the vertical scope, meaning choosing the rows.
We don't need to analyze a user's clicks from 3 years ago to predict if they are committing fraud today. We slice the data temporally, maybe keeping only the events from the last 24 hours. We're drastically reducing the volume of data moving down the line.
Next, the surviving data reaches the joining station. This is where the magic of the relational model happens.
This is where we utilize those foreign keys we discussed. We use SQL to instruct the database to align the records. We tell it to match the userid from the recent event stream with the userid in the state profile table.
And the database engine just matches these millions of keys in milliseconds, stitching the behavioral context to the user's identity.
It's incredibly fast.
But the granularity is still broken at this stage, right? We still have many event rows attached to one user, so the data has to move to the heavy machinery, the aggregating station.
Here, we instruct the engine to group all the raw event rows that share a specific userid into a single bucket. Then we apply mathematical functions to the bucket. We sum the transaction amounts to get total spend. We count the events. This is the moment the high-velocity event data is mathematically compressed into static features.
And finally, for advanced feature engineering, we run the data through the window functions station. This transforms features by looking at sequences.
Yes, window functions are incredibly powerful. Suppose you want a feature calculating the average time elapsed between a user's first purchase and their second purchase. In SQL, a window function allows the database to look at sequences and patterns with incredible efficiency without messing up the granularity.
So all of these stations, projection, filtering, joining, aggregating, windowing, are executed sequentially within a single, cohesive SQL pipeline. And when the script finishes running on the warehouse supercomputer, what rolls off the end of the assembly line is the final feature table.
It is a clean, rectangular grid of data. Every row is one user. Every column is a dense, highly predictive feature.
It looks exactly like that pristine Kaggle CSV file.
Yes, that is what you finally load into your machine learning model in Python.
And beyond the sheer computational necessity of using SQL, there's a secondary operational reason why this pipeline is mandatory in professional engineering environments.
A very important one.
Because in a real company, you do not work alone. You work on a team with data engineers, product managers, and other data scientists. The SQL query you write isn't just a retrieval command. It becomes the official, version-controlled documentation of how features are built.
That is a critical point about engineering maturity. Let's say you engineer a feature called adjusted lifetime value. If you perform all the mathematical transformations to calculate that value inside a messy Jupyter notebook, scattered across 20 disjointed Python cells, it is essentially a black box.
If you leave the company, the next engineer who inherits your model has no idea how that feature was actually defined.
Exactly. Did it include sales tax? Did it subtract refunded items? Did it count purchases made with gift cards? Nobody knows.
And if your SQL logic is messy, your feature logic cannot be trusted by the team. An undocumented feature is an untrustworthy feature.
And an ML model built on untrustworthy features is a liability to the business. But if that logic is encoded in a structured SQL pipeline, it is entirely transparent. Any engineer can read the query and see the exact mathematical definition.
They can see how you filtered out refunded items or joined tables to exclude gift cards.
The SQL code acts as the undeniable source of truth for how raw reality was transformed into an algorithmic signal. Professional ML engineers treat the SQL pipeline as a vital part of the ML model itself, not just an afterthought.
Wow. We have completely deconstructed the data universe today. Let's do a rapid, high-level recap of this fundamental mental model so it is permanently locked in your mind.
Sounds good.
We established that real-world business data does not exist in flat files. It is fragmented into relational databases. The database organizes the world by identifying core nouns, called entities, and giving them isolated tables.
Inside those tables, rows represent specific instances and columns store attributes which become our features.
Exactly. We analyze the concept of granularity, recognizing that the event stream stores data at a microscopic, high-volume level, while our machine learning models require a macro-level aggregated view.
We explored keys, primary keys as unique identifiers or hooks, and foreign keys as connectors to trace behavioral paths.
We contrasted the temporal nature of data, slow-moving state tables versus high-velocity event tables. And we established the golden rule, transforming everything via SQL by aggregating chaotic events to describe static states, which creates the final dataset.
Conceptually, you now understand how data lives inside these interconnected tables. So the obvious next question is, how do we actually look at it?
Right. Understanding the schematic is great, but writing the code is what makes you industry ready. So in our next lesson, we will cover the very first SQL operation used by every ML engineer. Select.
It's the operation that extracts the exact columns you need from massive tables.
It's essentially how you see data and extracting information from tables. Make sure you try out the exercise provided for this lesson to solidify these concepts. Write any questions or blockers you have in the comments below. We read them. And of course, please like, share, and subscribe so you don't miss the next step in becoming industry ready.
I want to leave you with a final, slightly provocative thought to mull over before our next deep dive. We talked a lot today about entities representing the real world. But think about this. What happens to your database and your ML model when the real-world definition of an entity changes?
Oh, that's interesting.
For example, what if a user used to mean one email address, but now it means a family sharing a single household account?
Like a streaming service.
Exactly. How would your tables and your features have to adapt to that new reality? Reality is never static, which means our data models can never truly rest.
When the definition of reality changes, the digital universe has to be rewritten. It's a terrifying and thrilling problem. We will see you next time.